Okay, so up until now, we've been trying to add individual little electric fields that have been coming from point charges, and that has been strangely enough, it's hard enough to do that, but in real life, um, charges are generally spread out on top of a fairly large object. They're not little point charges that exist all on their own. We have instead what we call continuous charge distributions. Um, Sorry, goodness, why is this not showing up? Continuous charge distributions, where the charge is spread out. It's not discrete along some surface. And if when you have individual charges, you do sums of the x parts and the y parts and the z parts from each individual little charge. Now that you have some spread out charge, instead what you'll do is we have to do integrals of all the little parts that are coming from each individual little section of the charge, and do the integration. And so we get EX and EY and EZ, but instead of doing summations over discrete individual particles, we're going to do integrals over a distribution. And that probably sounds bad enough. But on top of that, for each situation that we're in, we actually have to figure out what these integrals need to be. We need to find expressions for what is DEX, what is DEY, and what is EDZ. Usually we don't end up having to do a three-dimensional thing. Usually it's just a two-dimensional problem, at least in Physics 112. Each situation that we're dealing with, each charge distribution, and each location inside that situation is generally a different mathematical integration that you have to do. We don't really get very far into this at all in Physics 112, which is probably good news to you. But this branch of physics is called electromagnetism. Physics majors will take at least one more class, probably two more classes at the College of Charleston on what we call E&M, which is what this class would be. The first part of this semester really is dealing with electricity and magnetism. So let's do an example. So say I've got this situation up here. I've got a little curved thing here. It's curved. It's just 1/4 of a circle. And I've got some positive charge Q, which is spread out over it. And the radius of this arc is capital R. So I've got some positive Q, which is spread out over this arc. And what we do is we define a thing called the linear charge density, which has got, it's Greek letter lambda, it's not wavelength, it's Greek letter lambda, where we say the charge over the length that the charge is spread out over, smeared out over. So in this situation, I have some charge Q, it's spread out over 1/4 of a circle, right? So the whole circumference would be 2 pi r, but it's just 1/4 of that. So it's just, it's 1/2 pi r. So the 2 of that comes up to the top. This is that 1/2 of the top. So 2q pi r. So that's what we call the linear charge density. It tells me how much charge there is per meter, essentially. And then I'm going to say, okay, there's some little dq. There's some little small amount of charge of q that's on some little section. So d sub ds is just this little section of the arc. And on that section, I multiply ds times lambda, and that tells me how much charge is on that little section, right? When we talk about integration, we try to separate things into little, what we call little chunks. And we, instead of having it be s, we call it d sub s. Instead of being q, we have dq, right? And so this says it's this little amount of charge, and this is how I quantify it. I say it's lambda times ds. Now, ds itself is d theta, which is this little tiny section here, times r, right? The arc length ds should be r, the radius times the the d theta, the amount of angle that's there. So, stick with me. dE, if E itself is kq over r squared, right? Then dE should be k dq over, instead of little r, this is capital R away, so it's k dq over r squared. dq is lambda ds, so I have k lambda ds over r squared, and then ds is r d theta, so I end up, and then an r can cancel there, I end up with that dE is k lambda d theta over r. That's my little, that's the dE. Each of these little parts up here, I can draw one here. There's a little electric field that's being produced by this, right? And it's equal to, goodness, the k, which is just our Coulomb's constant, times the lambda, which is the linear charge density, times d theta over r. Now, each of these little dE's, I can't just integrate this. It'd be wonderful if I could just say E is dE, and I could integrate that. But it turns out that each of those little dE's actually point in different directions. If I look at my arc here, right, there's this part of the arc right here. Let me show this in black. So this part of the arc right here, which I have marked in blue, that's producing a dE that goes this way, right? A positive charge would be pushed away from that section. Whereas this one in the middle, it's producing a dE that goes that way. And then down here, this little section's dE goes this way. So they're going in different directions. So I have to actually split this dE into x parts and y parts. So my dEx is dE times the cosine of this theta, which is just our regular theta measured from the positive x-axis. And I wrote it as a negative because notice that all of these are actually pointing, right? All of these things are pointing down here. So they have a negative x part and a negative y part. These electric fields. That's what these negatives are here for. And then the y part's just dE sine of theta. Now I have a dEx and a dEy, and I can integrate them. So here my E sub x is the integral of dEx, and my E sub y is the integral of dEy. That's what I'm doing here. So I had to go and I had to make these things. I had to sit there and be like, what are these? So I'm going to say negative k lambda d theta cosine of theta over r, negative k lambda d theta sine theta over r. That's my dEx and dEy. And that's what I've got down here in the bottom. When I finally do the integration, I have to sit there and come up with limits of my integration. This is starting, and this is basically how far am I going in theta. I'm starting at 0 theta. This is my theta initial, and I'm integrating up to a final theta of pi over 2, right? That's how far my arc goes in theta. So I'm integrating from 0 to pi over 2. Once we get to this point, it's actually not that bad. So looking at these integrals, everything out here is a constant. K is a constant, lambda is a constant, r is a constant, and so I can bring those out front. And so I end up with is just the integral of the cosine of theta d theta. Same over here with the y part. I can pull this out, and now I'm just left with the integral of sine of theta d theta. Even hopefully you guys have gotten that far in calculus too. What makes these problems hard is not the actual integration, it's coming up with that dx and ey, right? I mean, that probably feels like Greek to you. Like this whole page, probably your brain is exploding. And I appreciate that. And we'll do maybe some more examples of these things as we go through. Anyways, the integral of the cosine of theta is sine of theta. And then I evaluate it at pi over 2 to 0. Sine of pi over 2 is 1. Sine of 0 is 0. And so I end up with negative k lambda r. Here, the integral of sine of theta is actually negative cosine of theta. But then the cosine of theta of pi over 2 is actually 0. So we end up with a negative 0. Subtract subtract a negative cosine of 0, which is 1, and so I still end up with a negative k lambda over r, which is what we said. We expect to have a negative x part and a negative y part, and so that our overall E that comes from this arc of positively charged Q is pushing this way on something at the origin. And so we could actually determine that our electric field at this point is this. It has a k lambda over r and the I negative j I hat, and a k lambda over r and the negative j hat. I can't stress enough that the reason we're doing this is to find the electric field at some location. Because if I know the electric field at that location, then I can find the force on a charge at that location. So say, for example, in our problem here that I had a Q of a positive 10 microcoulombs and the R was 0.1 meter. Going back and saying, well, that means my lambda, remember this was my equation for my lambda, would be this much. I can actually go and figure out what the electric field is at those points. I can say, well, that means the electric field is 8.99 times 10 to the 9 Newton meter squared per coulomb squared times that 6.366 times 10 to the negative 5 coulombs per meter over 0.1 meters. All that's going to be, we'll put the negative out front, I hat plus j hat. So just 1 second. So my electric field has equal components, both negative in the I and j hat directions. And if I say I put a charged particle there, say I put a 10 microcoulomb positive charged particle. If I put that at this origin location, the force on this 10 microcoulomb particle would be 10 microcoulombs times this electric field. And I'd end up with negative 57.2 newtons in both the I and j directions. That's the force on the particle caused by that distribution of charge. I could do the same exact thing. This is another part of that first problem. Instead of having just a quarter of an arc, now I have a half an arc, or half a circle, a semicircle here. I could do the exact same thing with the same dx, dex, and dey, but here, instead of having my limits of integration being 0 to pi over 2, my limits of integration are going from 0 all the way to pi. And so the only difference here would be different limits of integration. For me, looking at this, knowing that this arc by itself produced an electric field this way, I'm going to assume from symmetry's sake, that this guy would make an electric field moving that way, which is exactly opposite, equal in magnitude. And so in all likelihood, what I'm going to end up with is that this section and this section cancel each other, and what I really end up with is a net electric field, which moves straight down, right? And that's what I should end up with if I do these integrations. In fact, you can see that if I integrate this, I'm going to end up with the sine. When I do the sine of pi, I'll get 0. And when I do the sine of 0, I'll get 0. And then this is the e sub x part of this will end up being 0. Okay. This is our last sheet. And it doesn't have any math. It just basically says what I've been saying. This probably has you feeling slightly panicked in terms of why in the world are we doing all these little DEs and the DEXs. I'll do more of these next week, and I'll do some in class as well, but it can be extremely confusing, specifically in terms of knowing where to start in terms of say, this page right here, where I say things like lambda is Q over L, and then, what is D sub Q in terms of this lambda, and then recognizing that D sub S is R d theta, and then being able to write out what this DE, and then knowing that I have to actually get a DEX and a DEY to do my integration. And then finally doing those integrations. I think this part of the problem can seem unbelievably challenging in terms of knowing where to start. But I can't stress enough that you shouldn't panic at all. I'm not going to make a Hitchhiker's Guide to the Galaxy joke. But you really should not panic. And try to keep in mind as I'm going through this chapter and I do these, that what we're doing all of this work to be able to find the electric field. But that's really what we want to keep in mind, is just that what's important here is that the electric field is the analog of G. Imagine that if we didn't know G, back in Physics 111, in every single situation, if we'd had to figure out what G was, it would have been extremely difficult. And that's kind of where we are when it comes to electric forces. The electric field is nowhere in the universe is the electric field consistent to the level that G can be consistent near a big planet like ours. And that just makes it more complex to find, but it doesn't change the overall structure, which is that what we really need to remember is that the electric field is Q times E. But this can be very difficult to find. It can be ugly, but the nature is the same. The analog here is the same between, if you know G, you can get F sub G. If you know E, you can get F sub E. And it's just sometimes it can be really hard to find out what the electric field is. And yes, we'll basically we'll eventually kill ourselves to try to find E through this chapter and the next one after that. Okay, that's all for pre-recorded lectures this week. We'll be doing some more chapter 22 the following week. And of course, I'll be doing some of this in class as well.